Good evening, ladies and gentlemen. My name is Coufoudakis. I'm the Dean of the School of Arts and Sciences. And on behalf of Indiana University, Purdue University at Fort Wayne, and the School of Arts and Sciences, I would like to welcome you here tonight for the lecture by Professor Jack Horner. In 1982, the School of Arts and Sciences, as a result of its commitment to academic excellence and to community engagement, introduced a distinguished lecturer series, and we have been at it since then for about 19 years, having brought to the Fort Wayne community and to the university community distinguished speakers, nationally known speakers, and internationally known speakers from the humanities, the social sciences, and the sciences. We're pleased that you have joined us tonight, and after this evening's lecture and after this evening's discussion, there will be a reception at the lounge where you came in from, and I hope that you'll be able to stay and to join us. Before we go any further, I would like to ask Professor Jim Farlow, who will be introducing our speaker, and Professor Horner to join me up here at the podium for a brief presentation. That's all right. No. We know it's going to be good. It's the tradition to present our speaker with a certificate of appreciation for doing that. Thank you for coming all the way. Thank you.
Well, it gives me great pleasure to welcome to IPFW as our distinguished speaker, Dr. Jack Horner. Some of you got that one. Well, I've known Jack for about 20 years, and Jack is one of those outstanding people who he goes out into the field, and there may be nothing. I may have gone out in the same area and seen nothing in 200 square miles, and within 5 minutes of arrival, Jack has found the most wonderful fossil you can imagine that completely changes everybody's notions about what was going on in that rock unit. Well, this kind of talent has gotten him a lot of acclaim. He is perhaps second only to Stephen Jay Gould, and maybe even not even second to Stephen Jay Gould as the world's most famous paleontologist. He has, for many years, been working at the Museum of the Rockies with an incredible collection program, finding goodie after goodie in the rock record. And I've gone out there numerous times to measure all the wonderful things he keeps finding, and I keep hoping he finds more and never quits. But he's going to talk to us tonight about some of the things he's found in the field, but also, more interesting, the kinds of interpretations he has based on them from studies in the lab. So I think you're going to find your ideas about dinosaurs perhaps challenged from what they were before, and certainly stimulated. So with no further ado, I welcome Jack Horner.
Thank you, sir. Well, I'm going to ask you all to bear with me. I have a cold, and it came from Indiana. A couple of weeks ago, Jim came to Montana with a bad cold. And he gave it to one of my lab assistants, and she gave it to me. And she gave me instructions to come back here with it and bring it back. So I've brought it back. Anyone will take it. So, dinosaurs. I have to ask the question, is there anyone in here that did not see Jurassic Park? There is one. Well, I'm going to ask a harder question now. Is there anyone that actually saw The Lost World? Oh, that's pretty good. Did you know we had a third one, too? Jurassic Park 3? We couldn't come up with a name for it. Anybody see Jurassic Park 3? All right. So you know, you've got some information. You at least know that that, you know that Tyrannosaurus Rex eats lawyers? And for those of you who saw The Lost World, you also know that T-Rex eats people that disagree with me. See, some of you didn't get that because you didn't see it. But in the movie, The Lost World, there is the rendition of a paleontologist with a straw hat and a long beard. Looks just like somebody that disagrees with some of the things I say. And as the scientific advisor for that movie, it only seemed right. It seemed like a very good place to do that. It seemed like the way. I was having some problems with lawyers the first year, Jurassic Park, and then I was having some problems with this particular person the second one. And the third one, I wasn't having any trouble with anyone, so we didn't have anyone eaten. But this is just to remind Frank that we are making Jurassic Park 4. So, tonight, okay, that'd be great. What did we do here? There, good, thank you. All right. This is the T-Rex that ate the paleontologist. And, you know, those of us that like dinosaurs, I mean, we're fascinated, and the press often asks me, you know, why is it that people like dinosaurs so well? Why are kids so fascinated with them? And, you know, there's not much I can say. I mean, I can tell them why me as a kid likes them, and I can probably say why a few people like them, but mostly I think it's because, you know, dinosaurs were big. They were different, and they're gone. And so they're kind of imagination engines. But big is the one thing that we could really say about dinosaurs. These are the arms of a thing called Tyrannosaurus, one of a really huge dinosaur. But, you know, when we think of really big dinosaurs, we always come up with animals like Brachiosaurus, an animal that's nearly 100 feet long and 30 feet high. And we are finding dinosaurs now in other countries. There's a dinosaur out of Argentina called Argentinosaurus that is probably somewhere around 125 feet long. Enormous animals. And of course, that's one of the questions that we oftentimes like to ask ourselves is, how did these dinosaurs get so dang big? Well, obviously, they had enough to eat. And that's probably all there is to it. Well, I'm of the opinion that is probably all there is to it. They did have enough to eat. But what's curious about dinosaurs, and especially big dinosaurs, is the fact that they started out so darn little and got so darn big. If you see right here, what you're looking at here is a group of duck-billed dinosaurs, and these are the babies down here. The babies hatch out about 16 inches long, and the adults are about 35 feet long. So, a good biological question here is, how did these dinosaurs get so big? But not only how did they get big, how did they get big without getting eaten? How did they get through this period of being little? Duck-billed dinosaurs hatch out at about 16 inches long. All dinosaurs hatch out of eggs that are relatively small. There have never been any dinosaur eggs found that were bigger than a soccer ball. And most dinosaur egg clutches are somewhere around 20 to 30 eggs. So they hatch out of relatively small eggs, certainly for the size of the animal. They have not very many eggs. They don't, alligators can lay 50 eggs. So there aren't very many eggs. And when the babies hatch out, they're really tiny, and they've got a long ways to go. And of course, little animals are susceptible to being eaten. And so, with the big giant dinosaurs like the sauropods, it's a real curious thing that we have so many giant dinosaurs. And so, it has been one of my research projects recently, trying to figure out how dinosaurs got so big without having, and how they got so big without being eaten. So, what I'd like to do is just start you out with a little primer here. I know you probably missed the talk in 1988, most of you, when John Ostrom was here to talk about dinosaurs and birds. So, this is a diagram kind of to show the relationship of the amniotes, the animals that lay eggs on land, which includes mammals, turtles, lizards, snakes, crocodiles, and birds. And what I want to look at right here is that crocodiles and birds share a common ancestry. Crocodiles and birds are a group of animals called archosaurs, and dinosaurs are also archosaurs. So we're going to talk about dinosaurs, and since dinosaurs are extinct, we want to learn something about dinosaurs. What we want to be able to do is make comparisons with living archosaurs, which means crocodiles and birds. So our living archosaurs, which you can only see one of here, this is an alligator jumping up to eat a bird sitting in a tree. So these are the animals that we study. These are the living ones that we have access to. And if we look at a diagram of Dinosauria and the relationships of the different dinosaurs to birds, basically we see that birds are in a group of dinosaurs. And this is the thing that John Ostrom initiated back in the 60s, and it is something now that most paleontologists agree with. Birds are the descendants of dinosaurs. Birds are in fact dinosaurs, and the evidence that we have to support some of this, I'll just run through very quickly. Dinosaurs have upright posture, like they walk with their legs directly underneath them, like birds do, and not like alligators, crocodiles. And alligators have a semi-upright stance. So dinosaurs in this particular character seem to be most of the dinosaurs. In fact, all of them seem to be a little closer to the bird side of that diagram. Dinosaurs, their hind feet have a three-toed hind foot, like birds. There's a number of other characteristics. The pelvis of some of the advanced meat-eating dinosaurs have this three-bone architecture. That here's the bird Archaeopteryx, here's Velociraptor, very similar. We look at the hands of the derived theropods. You see a long middle finger. We see that same long middle finger in Archaeopteryx. They're not identical to one another, but they're closer to birds than they are to anything else. Same goes for the wishbone, the clavicles. The architecture of the clavicles is closer to birds than it is to anything else. It's not the same, but it's closer. If we look at, this is a dinosaur called Oviraptor, and it was recently found in Mongolia, and it's sitting on a clutch of eggs. And it's not sitting on a clutch of eggs exactly like modern birds do, but it's closer. It's more like how birds sit on eggs than any other animal. So it is a bird-like character, or we could say it another way. We could say that dinosaurs invented this way of sitting on eggs. Dinosaurs invented hollow bones, the three-toed foot, the funny way of folding your arms. Like you know how birds fold their wings. Dinosaurs, theropod dinosaurs folded their arms the same way. If we look at some of the dinosaur eggs, they're actually fat at one end and skinny at the other end. It's the typical bird-shaped egg that we see in a lot of dinosaurs. So we have a whole variety of characters, and including this character, in China recently, they've started finding a bunch of little dinosaurs that actually have feathers. And so we can see that dinosaurs invented feathers, and birds kept them, basically. So these are the characteristics that suggest that at least the theropod dinosaurs like Deinonychus and Velociraptor really are more bird-like than crocodile-like, if you were going to make the comparison between the two. So when we restore these kinds of dinosaurs now, we actually restore them very bird-like. And on the other side, when we think of the most advanced dinosaurs, we think of birds. So there is no such a thing really as extinct dinosaurs, except those that died. So if anyone asks the question, what caused the extinction of dinosaurs, you just answer, they died. So basically we have two different kinds of dinosaurs. We have avian dinosaurs, like this one, and we have non-avian dinosaurs. I sure wish I could give this gold to somebody. And we have non-avian dinosaurs, and the non-avian dinosaurs are, of course, the ones that really got gigantic. So we have dromaeosaurs, Velociraptor, Deinonychus, Troodon, things like that. And birds, and they share a common ancestor. Now, big dinosaurs. How did dinosaurs get big? That's our question. How did some dinosaurs get so big? And how did some dinosaurs get so little? That's the topic of my talk. So, to study this, you have to remember that what we really have with the non-avian dinosaurs are bones. We have the skeletons. And that's basically all we have. And when we take those bones out of the ground and study them and look at them, that's what they are. They're bones. We can look at the length of them, we can look at the diameter, but we really can't tell much about their growth unless we have a growth series. But we can look inside, and the internal structure of bones tells you something about how the animal grew. And so what we do is we take these bones and we cut them up. We take a perfectly good dinosaur bone after preparators have worked for weeks, maybe putting it all together. We take it in the laboratory and we cut it up. And basically what we're looking for is we're looking in this area that's red right here, in the cortex of the bone. And when we slice into it, you can see right here the marrow cavity with some crystalline material in it. This is the cortex. And when we make a very thin slice of the cortex and look at it under a microscope, it has some incredible structures to it. And these incredible structures represent basically the parts that you would see in a living animal. The holes right here, these openings right here, these are vascular spaces. They're where blood vessels went through the bone and some other tissues. There are little spots in here, all these little colored spots. Those are osteocytes. Those are actually the empty space now that used to, when the dinosaur was alive, those are the places where the bone cells actually existed. You can see a lot of colored, looks like these colored lines circling some of these areas right here. This is actually collagen in the bone. So we're looking at minerals, the mineral tissue of the bone. We're looking at the collagen. We're looking at the osteocytes, and we're looking at the vascular spaces, the vascular canals. And so when we're looking to try to figure out something about the development of the bone or the growth of the bone in a dinosaur or any other animal, this is what we look for. We look for the amount of vascularization. We also look for the amount of bone development around one of these vascular spaces. These things, this whole area around it is called an osteon. And so we look for osteonal development. And we look at the shapes of these vascular spaces. So we're looking for osteonal development, the shape of the vascular spaces, and how many vascular spaces there are. This is a relatively young animal. If we look at an older animal, we would see something like this, although this is not a dinosaur, but it has a structure very similar, so you can kind of see these black areas right here. These are actually the vascular spaces. They're the osteonal development of the bone around these vascular spaces is very mature in this particular animal, and so you see they've kind of squished the vascular spaces, although there's lots of these vascular spaces. So basically what you're looking at here is an animal that was growing very fast through time. Now, these things right here, these are lines of arrested growth. So this is the old part of the bone is down here, and the young part of the bone is up here, and that's the exterior of the bone. So just looking through this bone, you can tell something about the history of its growth. You can see that it grew very fast to right here, and it stopped for some period of time, and then grew very fast again, stopped again, then grew fast again, but here it looks like another line right here, and then it grew again, and there's another line, and there's a bunch of lines up here. Well, this right here is a 4-year-old elk, a mammal related to a deer, an elk, and those lines of arrested growth are actually annual lines, and we'll see those in other kinds of animals as well. This is a warm-blooded, fast-growing mammal. Now, what we've done is we've looked at ducks, we've looked at alligators, we've looked at emus and ostriches and all kinds of animals, and actually looked at the different kinds of bone that animals have and figured out how fast each one grows. And so here's a kind of bone where the vascular canals are longitudinal. They're lengthwise through the bone. And that grows the slowest. And here's the kind of bone we were looking at in the elk. It's this, we call it laminar bone. And the canals are mostly circumferential. In other words, they go around the bone. But they can go other directions as well. This is plexus. They call it plexiform. These sort of middle ones are, it's hard to tell one from the other, actually. But basically, longitudinal and laminar are the ones you want to pay most attention to, because one shows relatively slow growth, one shows relatively fast growth. But this is in adult animals, for the most part. Adult animals, not juveniles. Juveniles have very open bone, and it's hard to tell what shape their vascular canals will be. So this is the kind of thing we're looking for. Now, we do have growth series of some dinosaurs that got relatively large. This is duck-billed dinosaur Maiasaura. We actually have an embryonic. We have embryos. We have little ones we find in nests. We have larger juveniles. Teenagers, sub-adults, adults. We have basically a whole growth series. And here's an Allosaurus, a meat-eating dinosaur growth series. We actually have one now that's half this size, so we've got a pretty small one. So basically, we just take these bones and we cut them open and we look inside and we see what we can see about growth rates. And like I was saying, we make comparisons with modern animals. So we want to make a comparison to living archosaurs, so we have kind of a baseline. So if we look at baby alligators, look at the bones of baby alligators. Here's what they look like. Here's the marrow cavity. Here's the outside of the bone. And so what we're looking at right here is bone. Again, it's a young animal. It is growing pretty fast. Quite a few vascular spaces in it. Certainly a lot of vascular spaces until you get right up into this area, then it gets to be a lot less. This is a yearling. This is a 1-year-old alligator, baby alligator, and it was grown in the wild. So it's a pretty normal animal. If we look at an older alligator, what we see is here's the older part of the bone. We see some of these longitudinal vascular canals, and as we get further and further toward the outside of the bone, we get less and less of this vascularized bone, but the canals are all longitudinal, which means it's growing relatively slowly. And here are the lines of arrested growth. This is a thigh bone, a femur of an alligator, of a 7-year-old alligator. So this is typical crocodilian bone, alligator, crocodile, whatever, and it is an animal. It is growing. Alligators grow about a foot a year. They hatch out of their egg right around a foot long, and they're about 2 feet long the first year, and so forth. Now we can soup them up. We can actually make them grow faster. This is an alligator that I raised in Bozeman, Montana, indoors, of course, and we actually raised it for 3 years and got it up to almost 6 feet long. We had it double. Basically, it doubled its growth. It doubled it. It got about twice as long as it should have gotten, and we see good vascularization all the way through the bone. But again, it's still this longitudinal bone. So it is still growing relatively slowly compared to the elk that we were looking at earlier. Now, if we look at birds, we looked at ostriches and emus. Their bone looks significantly different. They have large open vascular spaces. This is, just a month old or so. As you know, birds, at least modern living birds, grow up full grown in 1 year, regardless of, or less. Littler birds in much less time. So here is a young emu. Here is the bone of a tiny bird, meadowlark. And again, you can see these giant open spaces. Very fast growth. They are growing very, very fast, and they are developing a lot of osteonal bone around these vascular spaces. But when you look at an adult, in this case a rhea, here are those vascular spaces and all this good osteonal bone that has squished these things. and you can see that they are circumferential, and that is very fast-growing bone. So it was growing very fast until it died. So this is very typical of a large bird, a large modern bird. Now, if we look at dinosaurs, we would expect that if a dinosaur was growing like an alligator, that its bones should look like the alligator. We expect that bone tissue would grow just as fast then as it does now. So if we have longitudinal bone, if we have bone with longitudinal canals, it should grow pretty much at the same rate for back in the days of the dinosaur as it does now. So if we look at the baby dinosaurs, their bones are extremely vascularized. The dark areas here is the bone, the white area is the vascular spaces. And so we can see that the baby dinosaurs are really growing fast, extremely fast. Even the vascularization percentage is greater than we see in any living bird. And if we look at large animals, large dinosaurs, this is an adult duckbill dinosaur, and you can see these longitudinal, or this laminar structure where the canals are going circumferentially. These are the rest lines, the lines of arrested growth. This is an animal that is 7 years old. Here's another dinosaur. You can see, again, all these canals that are this laminar bone. This is Tyrannosaurus Rex. And this is a skeleton of Tyrannosaurus Rex. This is as big as the skeleton of Sioux, and it shows no indication of slowing down. All the way to the edge of the bone, the animal is growing very fast. This animal is also 7 years old. This is a sauropod, a brontosaur. Again, we have this laminar bone. Here's one of the legs, and we have a couple more legs up here. Actually, it looks like this sauropod is slowing down, which is a good thing because this particular femur comes from a dinosaur that's about 80 feet long. So we do see some slowdown in growth in some of these dinosaurs that are really big. But what we see all the way up to the point where it starts slowing down is this laminar bone that we see in modern animals as growing extremely fast. Here's another one, ornithomimid with ostrich dinosaurs. Same thing, same pattern. We get lines of arrested growth, but we see this on either side. We see this extremely fast, rapid growing bone. So we plot it out on a graph here just to look at number of years based on those lines of arrested growth. The alligator grows, it's about 2.5 meters long, 5 years old. An ostrich grows up in 1 year, just like all other modern birds do. And sauropods look like they grow up probably 10 to 12 years, are pretty much, and they're very large sauropods. I don't know if there's such a thing as a full-grown sauropod. And the maiasaur, the duckbill dinosaur that we have the most information on, if we discount some of its early, if we assume that it's missing a lag of arrested growth, we get it up to about 7 years old as a full-grown adult. It takes about 7 years, and if the legs are all, if they're all faithful and they're all preserved, then they grew up at about 5 years. So basically, whether it's 7 or 5, dinosaurs grew to very large sizes very quickly. The duckbill dinosaur, Maiasaura, hatched out of its egg, and grew to somewhere around 9 to 10 feet the first year. 9 to 10 feet long. These are not the kind of animals you want to have as a pet. They eat you out of house and home, and then they eat your home. So basically, we can say that's probably. I mean, it makes perfectly good sense if a dinosaur hatches out of a tiny egg, and there's only 20 or 30 eggs, and they've got this huge size to reach, that they grow really fast to do it, because obviously, if you grow slow, then you're just meals on wheels for Tyrannosaurs and everything else that eats meat. So as far as getting big goes, how the dinosaurs got so big obviously has something to do with growing very, very fast. But dinosaurs include birds. And some birds are really tiny, like hummingbirds. And so, if the dinosaurs are their ancestors, and dinosaurs grew very fast, how did birds get so little? And so what we've been doing now is looking at birds and seeing how they grew, and seeing if the growth patterns of birds is anything like the non-avian dinosaurs. And one of the first things we went to is a moa, one of the big flightless birds. And a moa, what we did is we cut we actually, in all these dinosaurs, we don't just cut one bone. We actually, in all the animals we work on, we usually cut the femur, the tibia, and the humerus. But moas are flightless, and they actually don't even have any wings anymore, so we didn't cut the humerus off. Anyway, when you look at the moa, it has this typical circumferential bone, this laminar bone, but it also has lines of arrested growth. And basically what this means is that moas did not grow up in a year. It took them more than 1 year to grow up. But they're big birds, so that certainly makes sense. We also cut some bones of a thing called Diatrima, one of the big gigantic birds from the Eocene. And we found something very interesting in it. The bone, we really did not find laminar bone. We found kind of a messy looking bone that had a lot of longitudinal canals in it, and we found lines of arrested growth. And in fact, what we found was we've got a relatively fast-growing bone, certainly more vascularized than we see in alligators and crocodilians, less than we see in most of the dinosaurs and other birds, but growing along pretty well, and then really slowing down and laying down lines of arrested growth in this very non-vascularized bone. So it looks like Diatrima grew relatively slowly, and then as it approached adult size, grew very slowly, but didn't stop for a while until it was full grown, like most birds do. So this was interesting, and it's interesting because when we look at baby birds, baby meadowlarks and things like that, they grow very fast when they're young, and then when we look at their mature bone is actually non-vascularized, and I'll talk about that in a second. This is Archaeopteryx, and Archaeopteryx is a very primitive bird, and we would have loved to have gotten bone out of Archaeopteryx and cut it open, but you can probably imagine that museums don't like us. I have my own museum, so I can go and cut bones open, but when I go to other museums and ask them if I can cut the bones of their dinosaurs and rare birds, they don't even answer me. So what we did was we went out and we got a primitive bird called Confucius ornis. Now, there's a lot of there's a lot of controversy these days over commercial collecting, and a lot of it has surfaced since the skeleton of Sue was sold for $8 million. And so out of China has been coming an awful lot of dinosaur eggs and fossils like Confucius ornis. And they're illegal. If you see dinosaur eggs from China for sale, they are illegally out of the country. And so we certainly don't encourage people to buy these things. So what we've done is when we find some of these specimens for sale, we end up buying them, or we get donors to buy them, and then we give them back to the museums in China. And because we were doing this, they allowed us to cut up one of the Confucius ornis specimens. And so we did a serial sections through these Confucius ornis birds. And what we found is that they are growing very much like that diatrino. We have relatively fast-growing bone early in the bird's life, and then we get a rest line. So Confucius ornis, even though it's a small bird, a small primitive bird, did not grow up in 1 year. But it is longitudinal growth. You can see the primarily longitudinal canals. So this is a bird that is not growing very fast compared to the big dinosaurs, brontosaurs and sauropods and duckbills and all those things. So what we learned from this is that the primitive birds and maybe even some of the more recent birds grew a lot slower than the animals that we consider their closest ancestor. In other words, animals like Velociraptor and Deinonychus. They were growing much slower than these. And then when we look at the extinct birds, basically what we see is relatively fast. And I say relatively fast because it's nothing like the large dinosaurs or even some of the big birds of modern birds. Relatively fast, and then they lay down these lines of arrested growth, so it takes them more than 1 year to grow up in the extinct birds. If we look at modern extant birds, large extant birds like the rhea and so forth, you have this laminar bone, and then at the end of the bone you get what is called an EFS, and this is actually where the animal quits growing, and it gets a bunch of lines, but they're getting them up there because the animal grows up in 1 year. If we look at small extant birds, we don't have any evidence of rapid growth at all. We're basically getting what is called an endosteal layer that is laid down when the animal is full grown, and then we're getting the EFS, which is actually just this little area right up here. So all of this is missing, but we see that in the babies. We actually see it preserved in the babies. So what we believe is that birds, these little birds, are actually pedomorphic. In other words, the pedomorphic dinosaurs, basically. They are, at least their growth is pedomorphic, which means that they are retaining juvenile growth characteristics all the way till they're adults. And this is the reason that they are so little. So, if we look at hummingbirds, for example, a hummingbird, or some of the little birds like meadowlarks and robins and so forth, grow up in just a matter of weeks. But they're still maintaining that same growth rate that we see in non-avian dinosaurs. The primitive ones started out relatively slow growing, and the more derived ones now are back to those same growth rates that we see in non-avian dinosaurs. And so they're able to grow up in very short periods of time, hatch out of their eggs, full grown in just a few weeks. So, dinosaur growth is based on dinosaurs growing. No, take that back. Dinosaurs got big, fast. Primitive birds reached their size growing relatively slowly, and tiny little birds, again, adapted for rapid growth over very short periods of time. And that's why dinosaurs got big, and so that's it. So, anyway, I'm about to lose my voice and my mind. Dinosaurs provide an awful lot of information. And it's not just from their skeletons, it's from the internal structure of their bones. And so it is the reason that we continue going out in the field. With this interest in trying to figure out how dinosaurs grow, I was interested in seeing if I could collect a number of animals from one particular environment. And so recently I've undertaken a thing called the Hell Creek Project, where we're attempting to find a number of animals preserved at particular time horizons. So we can look at varieties of dinosaurs growing in the same environment and see if we get the same kind of patterns. And I originally set out to find duck-billed dinosaurs, and try as we might for 3 years, we found one duck-billed dinosaur and 8 Tyrannosaurus Rex skeletons. And that, to me, is just a bummer. I like duck-billed dinosaurs. Jim Farlow, on the other hand, he seems to like tyrannosaurs. And I wasn't looking for tyrannosaurs, although we're still looking for that little tyrannosaur. He wants one with, he wants one with skin impressions and gut contents and every impossible kind of thing you can imagine. So, this is sort of how we're moving into this growth project, looking at how various individuals grew in particular environments, sedimentary environments. So, in the end, it is with dinosaurs and with all these other extinct forms, we get little bits of information that we try to piece together and figure out the lives of dinosaurs and how they grew and something about their physiology and just about anything we can imagine we try to get out of them. But that's what it is. It's hypotheses, and even though I might make hypotheses about how dinosaurs grew and about dinosaurs being warm-blooded, any one of you can come along and falsify virtually all of my hypotheses, and in the end, we'll learn something new about dinosaurs. Thank you. apologize because I'm not doing well. Are there any questions? You know, if there were more kids in the audience, there'd be one question.
Did you find evidence of bone resorption?
Bone resorption? Yes, of course. In what?
Well, I just didn't notice any in the photographs that you showed. You showed the arrested development.
Oh, you mean on the legs?
Yeah.
The legs are arrested growth. Yeah.
Well, when you find like bones of Velociraptor, how big are usually those slashing claws on the?
How big are the slashing claws on Velociraptor?
Yeah, on the feet.
Not as big as the ones in Jurassic Park. You know, that was a big plastic. Did you notice that was a big plastic? In fact, I had to tell you a story about that. Steven Spielberg wanted a cast. He wanted a Velociraptor to put in the beginning of Jurassic Park, and he wanted an impressive one. And so I went out and got the very biggest one there was. I cast of it. I put it in the ground. And he came out one day and he said, "It's not big enough." And I said, "Well, that's too bad. You know, that's the biggest one there is." And so he just got rid of it and made a styrofoam one. And that's what you can do in the movies. So a Velociraptor slashing claw is about that big. Now, Utah Raptor, on the other hand, has a slashing claw that's about that big. What do you think? It's okay? It has to be okay. Yes?
Now, that Tyrannosaur was almost as big. It was as big as Sue. It was 7 years old, and it didn't look like it was finished growing. How big?
Say that again?
That Tyrannosaur bone you're showing us. You said the cross section came from the Tyrannosaur, or as big as Sue. It was 7 years old. Did the theropods grow full grown at 7 too, like that?
We don't know. We haven't got one with one of those EFS, the lines where they stop growing. We haven't found one yet like that.
So how big possibly could?
Well, they probably get real big. You know, when we go out and find dinosaurs, you know, T-Rex is one of the most common dinosaurs. There are a dime a dozen. We have 11 of them at our museum. But, yeah, well, I might think about that. Most dinosaurs, you know, we don't have, a Stegosaurus, there's only a couple of skeletons. I mean, most dinosaurs we don't have very many of. And when you think about, we go out and find a dinosaur, chances are pretty good we're going to find an average size one. You know, if you went out into a population and looked for really old people, it would take you a while to find really old people, right? So it's sort of the same thing with dinosaurs. I mean, you know, as you go out and find more and more and more, chances are you're going to start finding some of the older ones, which are bigger. So that's why we need to keep going out and finding more and more dinosaurs, because then we can start finding some of the bigger, rare ones. So Argentinosaurus and some of these really gigantic things that are people are starting to find now. We're probably starting to get into some of this, the big ones finally. We found a duckbill dinosaur. The one duckbill dinosaur that we found is gigantic. It's bigger than any of the T-Rexes. So that's probably why it preserved, right? I mean, it was bigger than the rest of it. It didn't get eaten. All the rest of them got eaten. That's why we can't find them.
What are your thoughts on predator-to-prey ratio?
Predator-to-prey ratios? I don't have a thought on them. The guy that had a thought on them got eaten. What?
I've heard that you find a lot more prey dinosaurs than predator dinosaurs.
Well, the fossil record is kind of a funny thing. It's not like going out into a modern environment and counting the number of predators and prey. I mean, you're kind of at the mercy of what you find. So, our predator-prey ratio in the Hell Creek Formation is really skewed right now. 1 duckbill and 8 T-Rexes. It's just not right. We're pretty sure that's not right. Yes.
I've been hearing a lot of stuff recently about T-Rex being a scavenger.
That's right. That's true. Yes.
What dinosaur had the biggest claws?
What dinosaur had the biggest claws? Well, remember that picture I showed right at the very beginning of those big arms?
Yes.
That's a thing called Tyrannosaurus. It definitely got the biggest claws. They're about that long.
There was one dinosaur I looked up in my book, and it had these really long claws about the size of its neck.
About the size of what?
It was the size of its neck. It was like a sauropod, but walked on 2 legs.
Yeah, that's a Tyrannosaurus. That's what those big arms were from. Yeah, same animal. That's good. Where are you going to go to graduate school?
Who are you sending them?
Yes.
Did you ever find a dinosaur with stomach contents?
A dinosaur with stomach contents. Well, there are some dinosaurs that we find sometimes that look like they have stomach contents, but it's really hard to say. I mean, you're looking at a skeleton basically, and so after the skeleton is rotted, things can wash into the area where the stomach was. I mean, it's hard to say what is actually from the stomach and what washed into the stomach. We've got a great skeleton, beautiful articulated skeleton of a duck-billed dinosaur with a 3-foot-long garfish in its stomach. Now, obviously, the duck-billed dinosaur didn't eat the garfish. And in fact, when you look at it really carefully, you can see that the garfish came into the bloated carcass probably right through the back door. Yeah. But stomach contents, there are reported. Take your cold back. There are reported stomach contents of conifer leaves and things like that. And the coprolites, fossil done, have a lot of conifer parts in them as well, at least the plant eater. And then, of course, we do get coprolites from meat-eating dinosaurs that have bone chunks in them, things like that. Yes?
Do you look at the bone development of snakes at all? Those similarities?
The bone development of
Snakes?
snakes? Well, they don't have a femur or a tibia or a humerus. So, pardon?
The way they grow.
The way they grow? Well, no, I have to admit that I haven't looked at snakes. Right.
I'm convinced, Jack, they grow real fast. And they have a very similar laminar structure to birds. And now, there's another leap you make. You say that this makes them endothermic. Why that leap? What's the thing that necessitates that second leap? Maybe that bone growth is characteristic of rapidly growing dinosaurs, and it is still existent in their descendants today, the birds. But does that mean they were also endothermic? Where's that leap there?
Well, the leap is only there because we don't have that kind of bone in any animal. It's only found in warm-blooded and endothermic animals. That's the only reason. We do not have that kind of bone in any other animal except a warm-blooded animal. Mammals and birds.
If you look at the giant reptiles, oceanic reptiles like Ichthyosaurus and so on,
Yes.
you look at them,
Yes.
do they have this type of bone too?
No, not at all. No, it's zonal lamellar, just like the crocodilians or Archaeopteryx.
They have pretty rapid growth too.
Yeah, well, they still have zonal lamellar bone, and they have parallel fiber bone. Yeah, no, we're looking. We actually are looking to falsify our hypothesis before one of these younger people comes along and does it for us. Yes?
Have you noticed anything when you're looking at the bone where you start determining gender towards the
Genders? No. But it's an interesting question, and modern birds, before they lay eggs, before the female lays eggs, it actually stores up some calcium in the marrow cavities of a lot of the bones. And so dinosaurs that we've actually found sitting on their eggs, and there's a number of them now, we've cut their bones to see if they're storing calcium. We haven't found any yet. But it'd be interesting. Of course, might be like ostriches. Ostriches, the males sit on the eggs. I don't know how that happens. I don't know how that female got that. Well, that's a good question, whether they're actually sitting on those eggs. They're in exactly the same position. I mean, they're literally in the same position that modern birds are in when they sit on their eggs. And again, it's that comparison. There's it's the most the most sensible explanation for the way they're sitting there. Is that they're sitting there for the same reason that birds sit there.
The birds have feathers
Well,
to keep the eggs warm. Now, would there have been an extra skin flap or something that would warm the eggs and protect them?
Oviraptor, there's evidence of feathery structures on Oviraptor, which is the dinosaur sitting on the eggs. In fact, they're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But and Jim can tell you, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible that a dinosaur could actually plant his feet in that hole. When an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible that a dinosaur could actually plant his feet in that hole. When an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it. It just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle, and so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space in the eggs. In fact, they're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space, sit right. In fact, they're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole. When an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space, sit right down over the top of the eggs. Feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. It hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that the dinosaur sitting on the eggs. In fact, they're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, I mean, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. I mean, it hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space in the eggs. In fact, they're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, I mean, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. I mean, it hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space, sit right. In fact, they're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, I mean, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. I mean, it hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space, sit right down over the top of it. They're starting to find, feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, I mean, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. I mean, it hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space, sit right down over the top of the eggs. Feathery-looking structures on a lot of the small dinosaurs. None of the big ones, but the small ones. And of course, that brings up the question of, how the big ones incubated their eggs, which is a good question. It's hard to imagine a 12,000-pound T-Rex sitting on its eggs. But, and Jim can tell you, I mean, that's, when an ostrich sits on its eggs, it actually doesn't sit on the eggs. I mean, it hovers, it sits down on it, it just sort of squats down over top of the eggs. It doesn't really, rest on them. So, maybe a T-Rex has got this great big huge pubic boot, and maybe just, if you've ever seen some of the dinosaur nests, the eggs are in a big circle. There's a big empty space in the middle. And so, it's plausible the dinosaur could actually plant his feet in that hole, in that empty space, sit right down over the top of the eggs. Where's our artist? We have a dinosaur artist here somewhere, don't we? Oh, there. See now there. See if you can position a T-Rex over 30 eggs without making omelets.
It's the naked blue brood pouch that doesn't have any feathers that's actually warming the eggs. The naked brood patch is a naked area without feathers that's very highly vascularized that's used to warm the eggs by an incubating bird, not the feathers. The feathers, as a matter of fact, are pushed out of the way so that the naked skin and the brood patch can come in contact with the eggs.
So there you have it. T-Rex can do it.
All you have to do is have a vascularized skin surface that gets warm blood.
Well, we have that, right? Okay, well, maybe they could do it. Over there. Yes?
Do different time periods have different size rates?
Say that again?
Do different time periods, like the quaternary or tertiary periods, have different growth rates?
Oh, you mean did animals grow at different speeds in different time periods?
Or what I'm trying to say is that...
Well, that's a really good question.
That was his question, right?
Huh?
I think that was his question.
Yeah, I don't think they did, but it's a really good question. I don't know that anyone's tested that question. Have you tested that, Jim? Well, see, you could do your undergraduate work here, and then come to Montana State. Okay?
Is Archaeopteryx the oldest known fossilized?
This what?
Archaeopteryx. Is that the oldest known fossilized, bird? And how many of them are there?
5? 7? 7? Yeah, it's the oldest until they date the Chinese beds. I don't know if they've quite done that yet. Yes.
Early on, you kind of somewhat flippantly said that the dinosaur growth rate was directly related to the amount of food they had available. It's kind of a tenet of ecology that if you have a lot of food available, you're going to have a lot of food eaters. They will reach a number of carrying capacity. I mean, how serious were you when you suggested that?
Well, I assume that you're not going to get very big if you don't have enough food.
But you're also not going to get very big if you have a lot of food and there's a lot of competitors for it.
That's true. Yeah, Joe and I were talking about that actually. One of the things that I've been people have suggested this before, and it seemed like you look at the dinosaur record, it looks like there's dinosaurs running over the top of themselves. I mean, all different kinds. But we've started doing some really high resolution stratigraphy and sedimentology in some of these formations, and we can't find evidence that there were a lot of different species living at the same time. In Montana, we've got the Judith River Formation, and you go to the record, the fauna of the Judith River Formation. It's got all kinds of dinosaurs in it, but you start looking at the resolution, you start resolving the formation into actual some depositional events. We could get it into a regressive and a transgressive phase, and the regressive phase has one kind of duckbill and one kind of horned dinosaur, and then a variety of meat-eating dinosaurs of different sizes. So, as we start to resolve some of this thing, we're starting to find that there aren't nearly as many dinosaurs living together as we once thought.
Are you finding the lowest trophic level numbers of dinosaurs that you're finding, regardless of predator-prey. I'm just saying, the trophic biosphere is pretty well established. So you're talking about quite a few top carnivores and a few second-level herbivores. Are you finding also the bottom trophic levels?
Like?
Lots of plants.
No. Well, I mean, again, it depends on where you are. I mean, generally, you get good bone fossilization in alkaline environments, which does not preserve plants very well. And you get good plant preservation in acidic environments where you don't necessarily get good bone preservation. So I'm not sure you look out at our area where Egg Mountain is, where we get all these nesting sites, babies and eggs, and I mean, the preservation is wonderful. We don't find any plants. So, I mean, we have root casts. We certainly have indication of plants being there, but we don't have the plants. What? How long have I been studying dinosaurs? A long time. How old are you? Huh? 11? Well, probably about as long as you will if you just start right now and go till you're almost dead. 35 years? That's scary. Well, that's how long I've been reading about dinosaurs, thinking I'm studying dinosaurs. It's hard to, you have to go find dinosaurs first, and that takes a while. And then you have to come up with a pretty good question. You know what I mean? To study it. You like dinosaurs? Yeah? You like have a favorite kind or something? No? Okay.
We'll take one more question there, and then we have a reception afterwards.
What sort of evidence? I did see Jurassic Park 3. And notice they have the T-Rex nesting sites. What do we know about T-Rex?
Nothing. We don't know anything about T-Rex nesting.
That was just for fun.
The whole movie is for fun. Jurassic Park, let me tell you, they're fiction. None of that's true. None of it. And the only reason they have a scientific advisor is, I don't even know why. They didn't need one. I mean, I'm glad they did because they donated a lot of money to my research project. That was good. But, Steven Spielberg doesn't listen to very many people. I mean, I told him a lot of times. I said, no, that's not right. And he just looked at me and kept on going. But that's okay, because he's made good movies. And I was not interested in having him make a documentary. So.
Steven Spielberg may not listen to anyone, but we hope you'll listen to us and stay around for crunchy cookies.